heat capacity is the amount of energy required to raise the temperature of an object by 1 degree Celsius. So it's the heat absorbed over the increase in temperature. We have two types of heat capacity that we'll be talking about: specific heat and molar heat capacity. Specific heat capacity is the amount of energy required to raise 1 gram of a substance 1 degree Celsius. And molar heat capacity is the amount of energy required to raise 1 mole of a substance 1 degree Celsius. So our main units are joules per gram degree Celsius or joules per mole degree Celsius. It could also be kilojoules or it could be Kelvin. Remember that your change in temp in Celsius and Kelvin are going to be interchangeable. Because if we go from 20 to 30 degrees Celsius, that's a change in 10 degrees Celsius. While if we went from 293 to 303 Kelvin, that's also a 10 Kelvin difference. So here it says water has a specific heat capacity of 4.184 joules per gram degree Celsius. What's water's molar heat capacity? So if we're to write this out, the only unit that we're changing is grams to moles. Well, we can convert grams to moles like we've done in previous units, and we're talking about water. So 1 mole of water is 18.016 grams from the periodic table. Notice that my grams then cancel out, leaving me with joules per mole degree Celsius. So we get 75.38 joules per mole degree Celsius. A calorimeter is an object used in lab to determine how much heat is associated with a chemical reaction. One type of calorimeter is 2 coffee cups nestled within each other. Coffee cups are often used because they aren't going to absorb or release any energy or very little energy from the reaction. So the reaction that's taking place in the cup isn't losing energy to the cups. Another one that we use sometimes is an aluminum can, but the aluminum can will absorb some of that energy. The energy lost by one object has to be equal to the energy gained by another object. So we have an equation. We have Q equals mCp delta T. We use that one when we have just one substance. Q is going to be our heat. M is mass. Cp is the specific heat capacity. And temperature is the change in temp. If your mass was in moles, then we could use the molar heat capacity. When you have two substances, heat lost has to equal heat gained, or energy released has to equal energy absorbed. And so we're going to do negative MCAT is equal to MCAT, or MC delta T equals MC delta T. The side that starts at the higher initial temp is going to be the side that gets the negative, because it's going to be losing energy while the other substance will be gaining energy. So the first thing we need to decide is if we have one substance or two. They gave us joules, which is Q, and the only time that they can give you Q is if we have our just one substance with water. So we're going to use Q equals mCp delta T. We're looking for the final temp of water. Final temp is related to the change in temp, so we need to rearrange. So delta T is equal to Q over mCp. Our Q was 596 joules. Our mass was 29.6 grams. And our Cp is 4.184 joules per gram degrees Celsius. Our joules cancel out, our grams cancel out, leaving us with degrees Celsius. So we get 4.81 degrees Celsius. It says that the heat is added to the water, so our final temp should be higher than what we started with. So 22.9 degrees Celsius plus 4.81 gives us 27.7 degrees Celsius is our final temp. Go ahead and pause the video and figure out if you have one substance or two and what you're solving for. So this problem, we have iron and we have water. So we have MCAT equals MCAT. And we need a negative on one of the sides. It says iron is heated to 100 and it's placed in water at 21. So iron should be the side that starts with the negative, and water is going to be the side without the negative. And I'm trying to find the CP of iron. So you could rearrange. I'm just going to plug everything in. So I have negative 5.037 grams. I don't know the CP. And delta T should be your final temperature minus your initial temperature. So the final temp is always the same for both substances. So we have 22.7 minus 21.2 for water. And for iron, it should be 22.7 minus 100. So that gives us negative 77.3 degrees Celsius for the iron. And then water, we have 27.3 grams. Our CP was 4.184. And our change in temp is what we talked about a second ago. So that's 1.5 degrees Celsius. So then, if you multiply the left side, I get 389 CP is equal to, and then I multiply everything on the right. And then to solve for CP, I divide by 389. So the CP is 0.44 joules per gram degrees Celsius, as it should be the same units as my water CP, because all other units canceled out. This one people often miss, where you're trying to solve for the final temp. So first, we have two substances. Although they're both water, they're water at different temperatures, which makes them different substances. So one substance is losing energy, one substance is gaining energy. Remember, the one that starts at the higher temp should be the negative. So that's going to be my water at 60 grams. And then my 20 gram info will go on the right. So I don't know the final temp, but I do know that the initial temp was 80 degrees. And then I've got 20 grams. And again, I don't know the final temp, but I do know the initial was 25. So final temp should be on both sides since it's affecting both of the substances, because it should be final minus initial. So there's two ways of doing this. Because this has water on both sides, the easiest way will be to scratch out the 4.184 on both sides. We also could multiply 60 times that and then do our next step that we'll be doing right now, which is distributing that out. But in this case, I can cross out 4.184, and then I'm multiplying 60 times TF and then 60 times negative 80. So I get negative 60 TF and then negative 60 times negative 80 gives me positive 4,800. Then I'm doing the same thing over here, so 20 times TF, and then 20 times negative 25 gives me a negative 500. Now I combine like terms. I like to get rid of my negatives, so I'm going to say plus 60 TF, plus 60 TF. So that's going to be 80 TF. And then I like to say plus 500, so that cancels out, and that's equal to 5,300. Then I divide both sides by 80. So TF is 66.3. My final temp should be between 80 and 25 because I'm mixing water at 80 and 25, so it's got to be somewhere between those two. Go ahead and pause the video and try solving this one out on your own. Restart when you're done or if you get stuck. So we only have one substance, so we are using this equation. And we're trying to find the final temp, so we're looking for delta T. So our Q was 120 joules. Our mass is 31 grams. And then our CP is 26 joules per mole degrees Celsius. So right now, the only units that cancel out are our joules. Grams and moles are not canceling, so I need one more step, and I need to convert my grams to moles. And I'm dealing with gold. So 1 mole of gold is 196.97 grams. So now my grams cancel, my moles cancel, I'm left with Celsius. So plugging that in, I get 29.3 degrees Celsius. But that's not my final answer, that's the change in temp. It says I have gold and I'm applying heat. So my temperature should be going up. So it should be 24.5 plus 29.3. My new temp should be 53.8 degrees Celsius. Go ahead and read this problem. Restart when you have read the problem. So this problem is a little bit trickier because it is a heat of reaction. So first we're going to find out how much heat was released from the experiment of mixing barium nitrate and sodium sulfate. The key here is look at what your specific heat's in. It says the specific heat of the solution. Well, the solution is once I've mixed my barium nitrate and sodium sulfate. So I have 1 liter of solution. Notice they also gave me the density of the final solution. So I've got 1 liter and then 1 gram is 1 milliliter. So basically I have 1,000 milliliters, so I've got 1,000 grams of solution. So now I can use Q equals MCAT because I'm trying to solve for Q. And so I need Q in my expression. My mass was 1,000 grams. My CP is given. And then my change in temp, it says it started at 25 and it increased to 28.1. So that's 3.1. So grams cancels, Celsius cancels. I'm at joules, but I want my answer in kilojoules. So I need one more step, joules to kilojoules. 1 kilojoule is 10 to the 3rd joules. And again, that info is on the periodic table reference chart. So solving that out, we get 12.97. We need 2 sig figs. Everything's in 2. So that's 13 kilojoules. So then it says, well, what's the enthalpy change? So enthalpy has to have a sign of barium sulfate. We have 0.5 liters and 1 molarity. So molarity is equal to moles per liter. So I've got 1 molarity is equal to 0.5 liters. So that gives me 0.5 moles of this one. And I have the exact same of the other one. It's a 1-to-1 ratio for both reactants, which means I should make 0.0 or 0.5 moles of barium sulfate. So I need my kilojoules on top. And I'm going to put how many moles of barium sulfate I have, which is 0.5. And that gives me 26 kilojoules. But again, if it's enthalpy change, I need a sign. And in this case, the temperature went up. And if temperature is going up, that means it's exothermic. So this problem is similar to the one we just did, except it's not a reaction as much as we're dissolving some ammonium nitrate. And we want to know what is the enthalpy change for dissolving the ammonium nitrate in the units of kilojoules per mole. So just like the last problem, we will need to get kilojoules, and then we're going to divide it by the moles of ammonium nitrate that we have. And just like the last problem, we're going to need a sign on our final answer. So go ahead and pause the video and try solving this one. Restart once you've solved or if you get stuck. So we're solving for Q again. First, we needed our mass. And remember, to figure out your mass, look at your specific heat. Our specific heat is of the solution. And our solution is both of these mixed together. So my mass should be 1.60 plus 75.0, giving me 76.6 grams. My CP, for my change in temp, unless I'm doing MCAT minus MCAT, I'm usually just doing bigger minus smaller. So 25 minus 23.34 gives me a difference of 1.66 degrees Celsius. I was subtracting, so I wanted 2 numbers after the decimal. And I need kilojoules again, so I might as well just go ahead and convert to kilojoules now. So joules to kilojoules. 1 goes with the prefix and 10 to the third. So we get 0.532 kilojoules. But again, we want kilojoules per mole. So we're going to take our kilojoules, so that was 0.532 kilojoules. And notice we want it in the dissolution of ammonium nitrate. So we want kilojoules per mole of ammonium nitrate. But we only had 1.60 grams of ammonium nitrate. So that's what's going to go on bottom, not the 76.6, because you can't find moles of a solution. You can find moles of ammonium nitrate or of water. And so we're going to convert those grams to moles. So 1 mole from the periodic table is 80.052. So I only dissolved 1.60 grams, but if I dissolved a whole mole of it, I would have 26.6 kilojoules. And again, this is enthalpy, so I need a change. my temperature went from 25 to 23. Temp decreased, and if temperature decreases, that means that it's endothermic. Endothermic means that it should have a positive sign. Alright, so here we have a marshmallow and we're burning it in a calorimeter. So we're trying to calculate the heat of combustion in kilojoules per gram. So go ahead and try this one. Restart when you're done. So we're using that Q equals MC delta T again, because again we're trying to find heat of combustion, which is going to be Q. Remember, look at your CP. Our CP is of water. Water is the substance being heated up and changing the temperature. So my mass needs to be of water. This time we're not combining because it doesn't say the specific heat of marshmallow and water because they're never actually coming in contact with each other. So we have our 50 grams of water, our specific heat of water, and then our water went from 23 to 27.4, so that's a difference of 4.4. And again, we need kilojoules, so I'm going to go ahead and convert that to kilojoules. So I have 0.92 kilojoules. But remember that we wanted the heat of combustion for the marshmallow in kilojoules per gram. So 0.92 kilojoules for every 0.350 grams of marshmallow burned. So I'll get 2.6 kilojoules for every gram of marshmallow that I burned. And technically this is negative because I'm combusting it. And notice that my temperature of water is increasing because the marshmallow is releasing heat. It's exothermic, the water is absorbing that energy. Alright, last one. This one is just explaining the difference in specific heat and what that means. So go ahead and pause the video and figure out which of these forms of water would require the least amount of energy to go up by 5 degrees. Restart when you're done. If you said water vapor, you are correct because it's only requiring 2.02 joules to go up 1 degree, while liquid, for instance, would take 4.18 joules per gram to go up a degree. So over twice the amount liquid water takes to go up a degree. And then solid isn't much more than gas, but solid would require a little bit more than gas to go up a degree. And since we want the least amount, we want the one that would have the lowest CP.